One of the things that can happen with an improper integral with an unbounded integrand is your asymptote, or perhaps asymptotes, might actually happen inside the middle of the interval of integration. So this is an example of that. Now it's the integral from -3 to 25 of this same integrand. So it's from -3 going off and a bunch of fairly uninteresting stuff to the right. And so now we've got some positive contribution here. We've got what looks like a rather smaller negative contribution here. And we want to see if it makes any sense to say there's some net signed area here or some contribution. So once again, the careful way to do this is we idealize taking a limit. And so, but the tricky thing is we have to separate it out into two pieces. Really what the first thing we do is we just say, anytime something really weird happens to our function in the middle, pretty much any kind of discontinuity in the middle of the interval, we just break it up. And that would have been true even if it was just sort of an ordinary piecewise function with a finite discontinuity. We would break it up into two pieces. That's kind of all I really need to say technically, because then it really reduces to the same ideas in part one. But let me go ahead and show you. This one is exactly what we just did before. So that is going to be plus 27 over 2. Okay. And then this one, how do we do this one? We still have to deal with the, we've reduced it now to something where the discontinuity, the asymptote, is on the exact right-hand side of the interval, this interval of integration. So we'll call that a t, and we'll do the limit as t. Now it's going to approach -2 from the left. Okay. So very similar to what we had before. I'll do it fairly quickly. Okay. This is going to be, when I do u equals x plus 2, those are going to change like that. And now this plus 2 is going to be -1. And this plus 2, same exact thing we had before, but now it's in the upper limit. It's going to be, or the upper end point, it's going to be t plus 2 there. And I can still rewrite this. Let me cheat a little bit. And just write as u to 1/3. So the thing here is that when you have to do this process, you're splitting the integral up, but the formula that you're using, this is a little bit different from a piecewise situation. The formula that you are trying to do an antiderivative of, it's going to be identical, and so it's going to feel a little duplicative, a little bit redundant, but you really do have to be careful about this. Okay, so now this is going to be, once again, so this should look really familiar from the previous part, u to the, ooh, that was a -1/3. Good catch, folks. Everybody who said, that's my -1/3, you're an idiot. Okay, 3 has u to the 2/3. This is all going to get evaluated from -1 on the bottom to t plus 2 on the top. Delete all this other stuff that doesn't make any sense anymore. And of course, at the end, we're going to add the 27 plus 2, 27 over 2. Okay, we're almost done with this guy. Let's just make sure, what does this mean if explicitly t plus 2 to the 2/3, and then minus 3 halves. Now we got to be careful. This is a -1 to the 2/3. Okay. And you could get a little freaked out with the negatives and the fractional powers, but when that is a fractional power and that's an even on the top, you can think of it as we're going to square that first. And, well, let me just go ahead and do that. So it's going to be -1 squared to the 1/3. Oh, so that's just going to be 1 to the 1/3. That can be a bit of a tricky issue, and calculators sometimes get really confused by that. Oh, and then plus 27 halves. Okay. Now, let's see. Very much like what we had before, because the negative exponent here has turned to a positive one, when I plug in t equals -2, this is a perfectly nice continuous function, and this evaluates to 0. So that dies. This is just a number, and so I get -3 halves plus 27 halves. And that's exactly what I expected from the picture. As long as we have some confidence that it makes sense to think about these in terms of areas, albeit of weird, infinitely extended regions, this was, down here, was a moderate negative number. It's canceling part of that positive off, and we end up getting 12, in fact. Okay, so that's the answer to this problem. Let me say one more thing, though. it's very tempting for people to say, well, what? I see some symmetry here. This looks like it's completely symmetric about this point, like a 180-degree rotation symmetry, essentially kind of an odd function symmetry, but around this point minus 2 comma 0. Is it true that the contribution from minus 3 to minus 2 and the contribution from minus 2 to minus 1 exactly cancel? And maybe all we're getting is the totally finite integral from minus 1 to 25. Well, in this case, that happens to be true. But here's what you don't want to do. Suppose I had one more integral, just what looks like it's symmetric there, minus 3 to minus 1 of dx over that cube root of x plus 2. Okay, can I say it's 0 just by symmetry done? It's really lovely when you can do that, because you don't even need to know the antiderivative, you don't have to do any u subs or anything like that. But in this case, that is very, very dangerous. Here, it happens to give the right answer. If you actually calculate this out really, really carefully, and again, here's what you would need to do, very similar to what we just did. You would have a limit as t goes to minus 2 from the left, and then this is a t here. And then you'd have a separate limit. Because that limit variable is a dummy variable, we could use, let me put it down here, the same variable. If you don't like reusing dummy variables, and that confuses you, you don't have to use the same variable, but it's totally legal. So there's the careful expression of the left-hand part and the careful expression of the right-hand part. Because those guys actually are finite and opposite, you actually do get minus 3/2 plus a 3/2. You can check it if you want to do this, redo this completely separately, but you really do get 3/2. And yes, in this case, the answer is 0. But really important, it's that these things have to exist independently on their own. In the next video, I will show a quick example, actually maybe a little bit in-depth examples of where that would get you into trouble. So you can't just say, oh, it's symmetrical, it's obviously going to be 0. You have to break it up into the two separate pieces, show that the pieces separately converge, and then the answer is whatever it is, it might be 0. So to summarize that, must separate, and each separate piece, in this kind of case where you've got a singularity in the middle of the interval, each separate piece must converge, must define a number for the entire improper integral to make sense. Well, to converge, let's say. All right.